Greetings everybody. Let's take a look at irrotational vector fields. So one question kind of becomes from the properties that we've seen before is there a way to tell that a vector field is going to be conservative? That means that it's the gradient of some function, so that we can take this shortcut in evaluating these line integrals. And a partial answer to that will be yes, and we can do it with one calculation almost. And so let's kind of investigate really kind of what that means. Okay. So remember that if the second partial derivatives were continuous, that the mixed partials were then going to be equal to one another, and that was Clairaut's theorem that we had. And this is kind of an awesome property, and this is really the basis of what we're going to use as kind of this quick calculation test to see if this is going to work. So suppose that we're given a vector field f, and it's got component functions p and q. And let's just say that we knew that p was going to be the gradient, or p was going to be the partial of f with respect to x, and q is the partial of some potential function with respect to y. Now, if everything is going to be continuous, if the second partials are going to be continuous, then that means that these guys are going to be equal. So the second partial with respect to y, then x, is going to be equal to the partial with respect to y, or with respect to x, then y is the same as the partial with respect to y, then x. So if we kind of separate those out, that's the partial with respect to y applied to the partial with respect to x, but that is p. The partial with respect to f with respect to y, that was our q. And so if we kind of look at the partial of p with respect to y, and that's equal to the partial of q with respect to x, then kind of a property of these things is that doing that calculation, if these guys are equal, it may mean that these guys are going to be, that our vector field is conservative. And so that's kind of one check that we can do. We can see if the partial of the first component with respect to y minus the partial of the second component with respect to x is equal to 0. And if we kind of do the same thing for a three-component vector field, well, now we've got three mixed partials, or three sets of mixed partials that are going to be equal. And so what does that reduce to? Well, the partial of q with respect to x is equal to partial of p with respect to y, or the partial of r with respect to x is equal to the partial of p with respect to z, or the partial of r with respect to y is equal to the partial of q with respect to z. Kind of rearranging those and putting everything equal to 0, that we've got these three equations. Well, we've got a handy little mnemonic calculation device to help us remember what this calculation was. And it looks something like the gradient operator cross our vector field f. And so what's that going to look like? We're doing this determinant of I, j, and k, partial with respect to x, partial with respect to y, partial with respect to z, partial p, q, and r for our component functions. And so if we do the determinant of each one of those, we get partial y, partial y, partial z, q and r, partial x, partial z of p and r, partial x, partial y of p, q. And so we kind of apply each one of these determinants. Well, the idea is we take our partial derivative operator and apply it to the function that's across. So instead of doing multiplication like we would with an ordinary thing, with our ordinary vectors, we'll do this as the derivative operator. So the derivative operator applied to the function. And so sure enough, that gives us our first component's our first equation, second component is our second equation, third component is our third equation for what we were getting. And this operator, this gradient operator, we call it del. So the del cross f is another name for the curl of a vector field. So if we look at the curl of this vector field, that the components of that one are our equations that are all 0 if this thing is a conservative vector field. And kind of coming back to our two-dimensional case, if we just have functions of p and q, where p and q are just functions of x and y, so the partials of z for all of those are going to be 0, then that just gives us our one single equation in the z component for the curl of our vector field. And so we kind of end this one with a notion that if we, for a vector field f, we say that this thing is going to be irrotational if the curl is going to be equal to 0. And so what we have so far is that we were operating under the assumption that if something was conservative, if it was already the derivative, then the curl gives you 0. So we know this direction. That's really Clairaut's theorem that gives us that if it's conservative, it's irrotational. And so the question that we have to answer now, does it work the other way? If we're irrotational, does that guarantee us to be conservative? And that's a question we'll have to answer in an upcoming video, so stay tuned for that.